Welcome back everyone. In this lecture we will continue with the characterization of conjugacy of elements in Sn. So first we will understand this conjugacy of cycles. So here is the first proportion. So if we take two cycles, let's call them sigma and tau, two cycles sigma and tau are conjugate in Sn if and only if their length must be same. So the length of sigma should be same as length of tau. So recall that length is nothing but the number of indices that appear in the cycle. Okay, if we write for example sigma equal to a1 etc. ak, so this k is actually called length of sigma. Okay, so here is the proof. So you take sigma to be a1 etc. ak, so this k is the length of sigma. Similarly, take tau to be b1 etc. bk, where k is again the length of tau. So we already actually looked at. So let's prove the one way. Okay, so let's take tau to have length k dash. Okay, because we want to prove that length must be same if they are conjugate. So for the forward direction, assume that sigma and tau are conjugate. So that means there exists some g in Sn such that g sigma g inverse is going to be exactly tau. Okay. So now if you write g as follows, g equal to 1 to etc. n and then g of 1, g of 2 etc. g of n. So then let us compute g sigma g inverse using the definition and then see what we get. From that it will become clear that tau must have the same cycle type, which is exactly length of tau is k. It is a cycle of length k. So the claim is, okay, if you take this g sigma g inverse, so this is going to be cycle of the following: g of a1 etc. g of ak. So it is cycle of length k, and that has to be exactly equal to g of a1 etc. g of ak. So how one can check this? This is just using the definition one can check. So let's rewrite what is this g sigma g inverse. So this is going to be 1 to etc. n, g of 1, g of 2 etc. g of n, and then you have this cycle sigma. So this is going to be just 1 etc. some a1 etc. a2 etc. some ak and so on n. So where a1 goes to a2, all other indices are fixed, and a2 goes to a3 and so on, and then ak map to a1. So this is your element sigma. So now here you have the inverse of this g inverse of 1 etc. g inverse of n. So now we want to compute what will happen to the product of these elements. Okay. So now let's look at, so we want to prove that this is exactly of cycle of length k given by these elements g of a1 etc. g of ak. So it cyclically permutes this g of a1 etc. g of ak. So in particularly if you compute what happens on g of a1, so you take g sigma g inverse and then compute it on g of a1, then let's see what it gives. It's going to give us g sigma g inverse of g of a1 will be a1. So then this is going to be g of sigma of a1 and then applied, like you apply g on that sigma of a1. So what is this? This is exactly equal to g of sigma of a1 is a2. So g sigma g inverse of g of a1 is exactly equal to g of a2. That's what it says. Similarly, if you compute g sigma g inverse g of a2, then you can see that this is going to be exactly g of a3 and so on. So now at the end, if you do this computation g sigma g inverse on g of ak, so then you can see that this is going to be exactly g sigma of ak, and sigma of AK is A1. So, this is going to be G of A1. Okay. That means G sigma G inverse cyclically permutes this G of A1 to G of A2 to etc. to G of AK, and then this G of AK is mapped to G of A1. So, this is what G sigma G inverse does on this G of A1 etc. G of AK. So, what is about outside? So, if you take some A which is not in this G of A1 etc. G of AK, so then we want to see what happens to that A. So, then let us compute this G A G inverse of A, then see what happens. So, note that if A is not in G of A1 etc. G of AK, then it is immediate that G inverse of A, this cannot be inside A1 etc. AK. So, that means this G inverse of A, it is not element of A1 etc. AK. So, that means the sigma must fix that. So, that means this is going to be equal to G of sigma G inverse of A, but this sigma fixes G inverse of A. So, you get G of G inverse of A, but what it is going to be exactly A. So, G sigma G inverse of A is exactly A for all A which is not in G of A1 etc. G of AK. So, that means, so we just observe G A G inverse is nothing but the cycle G of A1 etc. G of AK. So, now if G sigma G inverse. So, G sigma G inverse, if it is equal to tau, then it clearly says tau is also a cycle of length k. So, the length of tau is same as length of sigma. Okay. So, if and only if we want to say length of sigma is same as length of tau, okay, sigma and tau are both cycles. Okay. So, that is already given. So, that is okay. So, 2 cycles sigma and tau are conjugate if and only if length of sigma is equal to length of tau. So, there is no ambiguity in the statement. So, now we proved one way. So, if sigma tau are conjugate, then we proved that length of sigma must be equal to length of tau. So, now what is about the other way? The other way is also obvious. Suppose if you take tau which is of the form B1 etc. Bk, so then what you can do? You can define this sigma from In to In as follows. You just simply take this G maps this Ai to Bi for each I from 1 to k, and then all rest of elements G of A to A for all A which is not in A1 etc. AK. So, you divide In into 2 sets, which is first A1 etc. AK union the complement. So, whenever you take AI, you map AI to Bi using G, and whenever A is coming from the complement, you map it itself. So, that is your G. So, obviously, this is a permutation, okay, because the number of BIs are also k. So, now G is inside your Sn, and it is clear that G sigma G inverse is going to be tau using the earlier calculation, because G sigma G inverse is going to be G of A1 etc. G of AK, the cycle. So, that is exactly the tau which is B1 etc. Bk. So, this proves that if you take conjugate of a cycle, that is again a cycle of same length, and if you start with 2 cycle of having same length, they must be conjugate. So, now using this proportion we can prove our main characterization of conjugacy of elements of Sn. So, that is the theorem. So, what it says, so you start with 2 elements sigma and tau. Okay. So, 2 elements sigma and tau are conjugate in Sn if and only if the cycle type of sigma must be same as the cycle type of tau. Okay. So, one way is obvious. Okay, let us prove one way. So, if you assume that they are conjugate, then what happens? You write sigma as some okay, let us say sigma 1 etc. sigma r. So, this is the cyclic decomposition of sigma. So, then what happens if you conjugate the sigma by g. So, let us say there exists g in Sn such that g sigma g inverse is equal to tau, because we assume that sigma and tau are conjugate. So, it is conjugate under this g which comes from Sn. So, then it is clear that tau is going to be exactly equal to g sigma g inverse, which is exactly equal to g sigma 1 g inverse times g sigma 2 g inverse and so on g sigma r g inverse. Okay. Now, we already know that. So, these g sigma 1 g inverse. So, that is going to have same cycle type as sigma 1. So, if sigma 1 has length k 1, then g sigma 1 g inverse also will have length k 1. Okay. So, now we claim that this is indeed cyclic decomposition of tau. Okay. This star. So, we claim that this star is the cyclic decomposition of tau. So, why that is true? First of all, note that each element in this decomposition, they are all cycle. Okay. Sigma g sigma I g inverse is a cycle of length of sigma I. Okay. So, that is very much clear. Now, since sigma I and sigma j, they mutually commute. So, if you look at sigma I sigma j, they commute. So, that is if and only if they are disjoint. Okay. So, if you take two cycles, if they are disjoint, we have seen that they commute. Okay. In case if they commute, they must be disjoint. So, that you can take it as exercise. So, because they actually commute, so that forces that this g sigma I g inverse. So, that also commute. So, if you calculate this g sigma I g inverse g sigma j g inverse. So, you can see that this is going to be exactly equal to g sigma I sigma j g inverse. So, now sigma I is equal to sigma j, that forces that this is g sigma j sigma I g inverse. So, which is going to be exactly equal to g sigma j g inverse times g sigma I g inverse. So, using this commutation, okay, sigma I and sigma j, they are disjoint cycles, will imply sigma I sigma j they commute, and that would force that this conjugate of the sigma I sigma j by g, though those elements also will commute. Okay. And that will force that modulo our exercise. So, this g sigma I g inverse g sigma j g inverse, they must be disjoint. Okay. So, that proves that the decomposition that we have here, so that must be actually cyclic decomposition of tau. So, that means the cycle type of tau must be same as the cycle type of sigma, because the length of these elements again matches with the length of sigma i's in the original decomposition of sigma. So, this is actually the forward direction. So, what is about the converse? So, suppose if you assume the cycle type of sigma and cycle type of tau, they are actually same. So, then what happens? So, you can write sigma as some product sigma 1 etc. sigma of r, and then tau as some tau 1 etc. tau r. So, now note that, so this sigma i's, they are all disjoint cycles. Okay. So, basically you are partitioning 1 to n as some a1 disjoint union etc. disjoint union sum AR. Similarly, you are partitioning this tau with respect to tau, partitioning this 1 to n as B1 disjoint union etc. disjoint union BR. Okay. So, now the length of this A1 is same as length of B1 and so on. Okay. So, what we can do, so because this is going to be a partition of IN into two different ways, but more with the condition that the size of AI is same as size of BI. So, now what we can do, we can produce this G, so which is a permutation of 1 to n such that, so basically G maps, okay, so AI to BI. So, how it just maps, it just takes, you list AI as A1 etc. let us say AKI. So, then BI as B1 etc. BKI. So, then you just define G of this A1 is equal to B1 and so on, and then G of AKI equal to BKI. So, you define G that maps AI to BI. So, since G defines a bijective map from AI to BI, now patching this G together on IN, you can get a bijective map from IN to IN. So, now you have a permutation G inside Sn such that now if you take the conjugate G sigma G inverse, you can see that this is going to be exactly equal to G sigma 1 G inverse and so on G sigma R G inverse. Okay. So, because the sigma has this cyclic decomposition sigma 1 etc. sigma R. So, now it is not hard to see, if you take G sigma 1 G inverse, it is going to be exactly tau 1, because the tau 1 is nothing but given by that corresponding elements of A1. Okay. So, maybe I should use this I on the top, so that it becomes clear. It is related to the ith set AI. So, in particularly tau 1 will be A11 etc. So, it is a cycle, no comma, A11 etc. AK11. So, that is going to be your tau 1. So, note that your tau I is going to be A1I etc. AKI. Oh, sorry, the image of that. So, that is going to be G of this. So, which is nothing but B11 etc. BK11. Similarly, B1I etc. BKI. So, in particularly this G, if you take defined as follows, okay, using these conditions. So, then this G, when you conjugate sigma by this G, then you get obviously the product of tau i's, so which is going to be tau. Okay. So, then this proves that if you take sigma and tau, which are elements of Sn, if they are conjugate, then the cycle type of sigma must be same as the cycle type of tau. Okay. So, that gives actually characterization of the conjugacy of the elements of this Sn. So, this is somewhat very important result. From this you can actually conclude many interesting facts about the conjugacy classes of Sn. For example, the number of conjugacy classes of Sn must be the number of partition of n, because if you take some sigma and then you write it in terms of product of disjoint cycles, if you take sigma and then write it product of disjoint cycles, we have seen that this product of disjoint cycles corresponds to the distinct orbits of this 1 to n, where the orbits defined using that tilde sigma equivalence relation. Okay. So, that means you are partitioning this 1 to n as some smaller disjoint sets. Okay. So, in particularly if you look at the length of that set, which is 1 to n, the number of elements of that set. So that is going to be exactly equal to sum of all this length of the sigma i's. Okay. So that means, so once you write it in weakly increasing or decreasing order. So it is a convention that a partition is always weakly decreasing thing. So in particularly I can take this L of sigma r and so on etc. length of sigma of 1. Okay, this is going to be a partition of n, because our from this construction we always assume that the length is increasing along this order sigma 1 etc. sigma r. So in particularly length of sigma of r is going to be the largest and length of sigma of 1 is going to be the smallest. And so partition is nothing but a tuple of non-negative integers, okay, such that, so actually one can assume they are all positive integers, such that the sum of the length, okay, should be exactly in, and it is weakly decreasing tuple. So the summation length of sigma I ranging from 1 to r should be exactly n, and it should be weakly decreasing. If they satisfy these two properties, then we call it it is a partition of n. So now given sigma, the cycle type indeed determines a partition of n, and once you fix the partition of n, which is this tuple, which is the cycle type, so that actually determines the conjugacy class. So in particularly the number of conjugacy classes is equal to the number of cycle types, and which is equal to number of partition of n. Okay. So for example, if we take S4, so then the number of conjugacy classes in S4 is going to be the number of partitions of 4. So you can see that 4 can be partitioned as follows. So 4 is one partition, 3 plus 1 is another partition, and 2 plus 1 plus 1 is another partition, and 1 plus 1 plus 1 plus 1, that is again another partition. Okay. Again there is one more partition, which is 2 plus 2. Okay. So if you take partition of 4, then you get exactly 5 way of partitioning 4. Okay. So as I said before, it exponentially grows with respect to n. So this so, and it is easy to actually determine like representatives of for each conjugacy classes once you know the cycle type. Okay. So so now like so one needs to understand actually like what happens if you take these conjugacy classes inside an. Okay. So let me make one remark and then we'll proceed. Okay. So we need to understand sometimes how to work with alternating group as well. So so if you take for example like some element, okay, let's say sigma and tau, which is in an. Okay. So because sigma and tau are in an, so sigma and tau can be written as product of even number of transpositions. Okay. So this sigma and tau, if they have same cycle type, okay, then they must be conjugate in Sn. But that would not immediately imply they are conjugate in an. But one can actually determine when they will be conjugate in an. Okay. So I will do one special case. Okay. So that is very important for us to prove that to study the simplicity of an. Okay. So other things maybe I will write it in the assignment sheet and then you can try to check. But anyway, that's like if you are interested in the alternating group, then you need to explore that further. So let us see like so So, it is clear that if we take any 3 cycle, that must be element of AN, okay, because the 3 cycle is actually product of okay, 2 transpositions. So, if you take for example ABC, so this is a 3 cycle, then you can write it as AB times BC. Okay. So, this 3 cycle, so it is a even permutation. So, this can be easily checked. For example, you read it from the right side, what happens. So, if you take for example A, so A is fixed here. So, A goes to A here, okay. Then if you come to this A goes to B, then you can see that A goes to B. So, that means if you take A, B, C, so all rest of the elements do not matter. You can see that A goes to A goes to B, so A goes to B. So, now B goes to C here and then C goes to C, so B goes to C. So, C must go to A, there is no other option because C goes to B and then B goes to A in this. So, now you can see that this product of these 2 transposition is exactly equal to this ABC. So, if you take this 3 cycle, okay, which is a product of 2 transpositions. So, in particularly it is there in AN, okay. And if you take another 3 cycle, because they have same cycle type, they must be conjugate, okay. But now one can ask the question, so they are conjugate in Sn, okay, but whether they are conjugate in AN. So, that indeed true only for these 3 cycles and under the assumption that if n is greater than or equal to 5. So, here is the lemma, so which will be used later. If n greater than or equal to 5 and sigma dash or 3 cycles, okay, in Sn. So, then we know that they are conjugate in Sn from our previous result. But what one can prove? One can prove that this sigma dash is indeed conjugate to sigma under some element of A. So, there exists tau such that sigma dash is equal to tau sigma tau inverse for some tau in AN. Okay. So, this is indeed a very important result which is used in order to understand the simplicity of AN. Okay, how one can prove this? So, we already know that sigma dash they are conjugate in Sn. So, pick a omega in Sn such that omega sigma omega inverse equal to sigma dash. So, if omega is in AN, so then we are done. So, then there is nothing to verify. Suppose assume that omega is not in AN. Okay. So, now if omega is not in AN, so then what will happen, since you have this n greater than or equal to 5, okay. So, what we can do, so n is greater than or equal to 5, you write this sigma dash as some I1, I2 and I3. Okay. So, now n is greater than or equal to 5, you can choose Rs in In such that this Rs is different from I1, I2, I3. So, this Rs is disjoint from I1, I2, I3. Okay. So, once you have chosen something like that, now what you can do, you can simply take this tau which is omega times this Rs, this cycle. Okay. So, now note that omega is not in an. So, that means it is odd permutation. So, omega is odd permutation. So, that tells us that this tau is indeed even permutation. So, this is inside an. So, now compute tau sigma tau inverse. So, this is going to be exactly omega rs times sigma rs inverse omega inverse. Now, note that rs inverse is rs. So, this is going to be omega rs sigma rs omega inverse. So, now you can just do the calculation and then see. So, this rs and this I1, I2, I3 they are disjoint, okay, because that is how we have chosen this rs and I1, I2, I3 they are disjoint. That means they must commute. So, I1, I2, I3 and rs that must to commute, but sigma is I1, I2, I3. Oh sorry, I have chosen sigma dash. So, this is the sigma. Sigma is your I1, I2, I3. So, that means they commute, that means this element is actually become sigma. This is omega sigma omega inverse, because rs inverse they get cancelled and you get this. So, this is going to be your sigma dash. So, tau sigma tau inverse is going to be again sigma dash. So, we use the same omega that guaranteed from the earlier result, and then using that and just normalizing or modifying it, we get some element of an such that the sigma and sigma dash they become conjugate under that element of an. So, this just proves that any 2-3 cycles they are conjugate even in an, okay, when n is greater than or equal to 5. Okay, I will stop here. So, we will use these results that we have developed to prove simplicity of an for n greater than or equal to 5 in the next class. I will stop here. Thanks.